Hello and welcome. Today we'll get into section 6.2 on solutions about ordinary points. So in this section we're going to assume that we're starting in the form y double prime plus p of x y prime plus q of x y is 0. If we're not, go ahead and fix that first. If y double prime has any kind of coefficient, get it out of the way first. So point x naught is an ordinary point if p of x and q of x are analytic at x naught, else x naught is a singular point. So let's look at just a kind of quick couple examples what that means in English. So if I have y double prime minus 7y prime is 0, so q of x here is 0, p of x is negative 7. There's no value of x that would make me break any of our, for example, division by 0 rules. So this is ordinary everywhere. But if I have something like y double prime minus 1 over x minus 5, y prime plus 2y is 0, here we can see p of x negative 1 over x minus 5, q of x is 2, x equals 5 is a singular point. So if we were centering this around, say, x equals 0, we would have a radius of 5 that we could use. We couldn't keep negative infinity to infinity like the previous problem. Alright, so now that we are a little bit cleared up on what they're talking about as far as ordinary points, I want to look at a power series solution. Make sure I'm center okay. That's decent. Okay. So we're going to consider x plus 2, y double prime plus x, y prime minus y equals 0. So here our only singularity would be at x equals negative 2. So if I center this thing on 0, we're okay. No worries there. So we're going to assume that our solution takes the form of y equals sum from n equals 0 to infinity of c sub n x to the n, so a power series. Now our original has derivatives and second derivatives. We can do that with these. Y prime would be sum from n equals 0 to infinity of n times c sub n x to the now n minus 1 power. So we're just differentiating something of the form x to the n. That would be n x to the n minus 1. And this guy's along for the ride. Now in this one you might notice though, if I plug in n equals 0 here, the n equals 0 term is 0. So it would be more common then to write y prime is sum from 1 to infinity, so we're covering the non-zero terms. and c sub n x to the n minus 1 power. We do have a y double prime in there, so we'll go ahead and account for that as well. So y double prime, sum from 1 to infinity, since we're already starting at a 1, n minus 1, c sub n, x to the n minus 2. So we're just applying the power rule again, and all that stuff that was already a coefficient is still a coefficient. Once again on this one, if I plug in n equals 1, the term is a 0, so we'll start this guy at 2. So sum from n equals 2 to infinity of n by n minus 1 c sub n x to the n minus 2 power. So now that we have all of our ingredients, we have our y, we have our y prime, I'll go with the version where we've corrected the index, and we have our y double prime. We can plug those into that original differential equation that we've got. So we have x plus 2 times y double prime, we replace with sum from n equals 2 to infinity of n minus 1 c sub n x to the n minus 2 power. Do the same thing with the next term, so plus x times sub n y prime. We're starting now at 1, going to infinity, and c sub n x to the n minus 1 power, and then finally minus y itself. So that is sum from n equals 0 to infinity of c sub n x to the nth. And our right-hand side is still a nice pretty 0. So the next thing I'm going to do with this is a little bit of distributing. So if I distribute the x, I get sum from n equals 2 to infinity of n by n minus 1 c sub n x to the now n minus 1 power. Can you see why that is? I'm multiplying with the same base. I would add those exponents. X by itself is implied to be an x to the first, so 1 plus n minus 2 is n minus 1. I also want to distribute that 2, so plus, we can do the 2 inside or outside really. 2 sum from n equals 2 to infinity, n by n minus 1 c sub n x to the n minus 2. So those first two are now splitting apart the y double prime. Here I just have an x to distribute. So now I have sum from n equals 1 to infinity, n times c sub n. We now have x to the nth power. Again, this is an x to the first, and we're multiplying with the same base. Then we have minus sum from 0 to infinity of c sub n x to the n, and we're equal to 0. So it's getting a little bit better, but notice we want to be of the form x to the k with the same index, so that we can match all these up and put it under one roof, so to speak, in one summation. So let's see, 2 is our sort of biggest starting point, so we'll keep those guys as they are, and we'll go ahead and plug in the 1 here, plug in the 0 and the 1 here. So the first couple we'll just bring along for the ride. Apologies. Well, let's switch over to K first, then we'll adjust. It's faster that way. So for this first guy, k is going to be n minus 1. Equivalently, n is then k plus 1. So our starting point was at n equals 2, so k equals 1. So n is k plus 1, so we have k plus 1, n minus 1, k plus 1 minus 1 is just k. And we have c sub k plus 1, so n is k plus 1. And now we have the all-important x to the k power. Then we have plus, and we can keep the 2 inside or outside, doesn't really matter there. So on this one, our k is going to be n minus 2, so n is k plus 2 for this guy. So our starting point was at n equals 2, so k equals 0. That's where we're starting. So n is k plus 2, n minus 1, k plus 2 minus 1 is k plus 1. C sub n, c sub k plus 2. And we have our then x to the k power. Let's see, these guys both have x to the n already, so for these two, we're just going to say k equals n. So plus sum from k equals 1 to infinity of k c sub k x to the k minus sum from k equals 0 to infinity c sub k x to the k. And we're still equal to nice pretty 0. Okay, so starting to look a little better. All of these guys have an x to the k attached. We just want those indices to match, so we have 1s and 0s. So the ones where we start at 0, we'll find the 0th term and add it to starting the sum at 1. So that means this first guy is just along for the ride. So sum from k equals 1 to infinity, k plus 1 by k c sub k plus 1 x to the k. Now this one though, we're going to split up. So we're going to let k equal 0. So we have this 2 here. 0 plus 2 is 2. 0 plus 1 is 1. C sub 0 plus 2 is c sub 2. And x to the 0. So that was just plugging in the k equals 0. So this is what our 0th term would look like. And then the rest of them will start at 1. Okay, so there's no way I'm fitting the rest of this on one line, so I'll just put a little plus here and we'll follow along here. So our next one already starts at an index of 1. Hang on to it then. K equals 1 to infinity, k c sub k x to the k. This guy though, get that 0th term taken care of. So we would have minus c sub 0 x to the 0, and then minus sum from k equals 1 to infinity of c sub k x to the k. And finally we're equal to 0 at the end there. So these two lines really kind of belong on one line. I just don't write small enough to accomplish that goal. Alright, so I'm going to do a little bit of simplifying and sorting here. First of all, I'm going to grab any of the stuff that we had to just pull out from the summation notation. I'll bring that along first. So we have, let's see, we have 4 c sub 2 x to the 0 is just a 1, minus c sub 0 x to the 0 is also just a 1, plus our sum from k equals 1 to infinity, and now we're putting everybody under one roof at this point. So we have, let's see, we had our k plus 1 by k, c sub k plus 1. We're going to grab the x to the k's and just throw one of them all the way at the end of the line. That's why I started the bracket here. Then we have plus 2 of the k plus 2 k plus 1s multiplied by a c sub k plus 2. Then we had a plus k times c sub k and minus c sub k, all of that times x to the k, and we're equal to 0. Alright, I'll not be winning any awards for cinematography for this lesson. My apologies. Okay, so I know that's hard to read that as an x to the k at the end of the line. We just brought him to the end of the line, held on to everything else. So if this thing is ending up equaling 0, we can make a couple of assumptions that 4c2 minus c naught is equal to 0, and that the inside of this sum is also equal to 0. So we can also say that k plus 1 by k c sub k plus 1 plus 2 by k plus 2 by k plus 1. I'm not sure why I wrote k plus plus there. Let me just make sure on that. Yep, k plus 1. Yeah, 2 and a 1. Okay, double checking. All right, c sub k plus 2 plus I can grab a c sub k out of both of those guys and have a k minus 1. So that's also equal to 0. So basically we're going to be able to turn this into a sum. Really we're only going to identify kind of a handful of the terms. Not all of these turn out to be nice, neat, pretty functions, which is why we're learning this kind of messier method. So this one, even though it would be faster to get c sub 0 by itself, c naught by itself, generally we want the higher one by itself, so c sub 2 is c naught over 4. Highest on this guy is c sub k plus 2. We're going to get that one by itself. So I have 2 by k plus 2 by k plus 1 by this c sub k plus 2. It's worth opposite of k plus 1, k plus 2. K plus 1 by k. Apologies. K plus 1 by k, c sub k plus 1, and minus quantity k minus 1, c sub k. So c sub k plus 2, just divide out. So minus k plus 1 by k, c sub k plus 1, minus k minus 1, c sub k, over 2 by k plus 2, by k plus 1. So now we're just going to take a look at different values of k. Notice on our sum we start at 1, so we'll start at k equals 1. So at k equals 1, 1 plus 2 is 3, so we have a C3 there. So C sub 3 is opposite of 2 by 1, so just plugging in a 1 everywhere you see a k. C sub 2 minus 0 C sub 1 over 2 by 3 by 2. The C1 drops, one set of the 2's drops, so we have minus C2 over 6. C2, remember, was CO over 4, so we have minus CO over 6 by 4, so opposite of C naught over 24. So that's going to be one of the answers in our power series answer. Then we let k equal 2. So that would be then C sub 4. Again, just plugging in now 2's everywhere you saw a k before. So C4 opposite of 3 by 2 by C sub 3 minus k minus 1 is 1 times C sub 2 over 2 by 4 by 3. Well, C3 we have in hand, C2 we have in hand. We can write both of those with respect to C naught. Sometimes you'll end up alternating between unknown variables of C naught and C1. Sometimes the same one will keep cropping up. So let's see, we'll do a little bit of simplifying here. So you have negative 6 times C3, so negative 6 times negative C naught over 24, minus C2, C naught over 4, all over, that would be 8 by 3, 24. So let's see, so we have CO over 4 minus CO over 4 is 0, 0 over 24 is 0. So C4 drops out. 0. That happens sometimes. We'll do a k equals 3, and then we'll have to do a little flipping. Again, just subbing in a 3 everywhere you saw k before in here. In fact, I would encourage you to kind of pause the video and make sure that your end result on that agrees with what I'll come up with here. So C sub 5 opposite of 4 by 3 times C4 minus 2 by C sub 3 all over 2 by 5 by 4. So again, we have C4, we have C3, we can write those in simpler ways. So C4 is wiped out, so we can also drop out these 2's. So we have opposite of C3 over 20, and C3 is opposite of C naught over 24. Okay, so C3, yes, that's where I left off. So C3 was opposite C naught over 24, not 20. So C5 is C naught over then 480. And really that's enough terms to start writing our final answer So remember at the start of this, we said that our solution was going to be represented by the power series of n equals 0 to infinity of c to the n, x to the n. So y equals, we can at least write out the start of it. So c naught, x naught, c1, x to the first, c2, x squared, and we're going to do a little substitution. And we did through c sub 5. So c naught is just c naught, x is 0 is just a 1. Notice we never really came across the c1x, so that is still just going to stay parked there as c sub 1 times x. C2, C3, C4, C5, the rest of them were written with respect to C naught. So our C sub 2 was C naught over 4, and that was multiplied by x squared. Our C sub 3 was opposite of C naught over 24. C sub 4 was 0. And C sub 5, that last guy that we just came up with, C naught over 480. So we can kind of group them based on which arbitrary starting constant they have to find our y1 and y2. So y1, we can call that c naught times 1 plus 1/4 x squared minus 1/24 x cubed plus 1/480th x to the 5th plus dot dot dot. Y sub 2 is going to be c sub 1 times x. Not as fun and exciting, but still another of our starting solutions. So this should be enough to get you through. I had you pause on the 6-1 stuff. I wanted to cover all of the stuff with derivatives in one go, so to speak. So in 6-1, you should be able now to finish 31 to 37 on the odds. And in this is 6-2, 1 to 23 odds should be plenty of practice. If you have any questions, please get in touch with me. Otherwise, I'll see you next time. Stay safe out there.